The video you're about to see is a real-time recording made at a live ICRI technical session. It is important for you to realize that the remarks of the speaker do not necessarily represent the views of the International Concrete Repair Institute. This presentation is intended to refresh your memory if you attended the session and to allow you to benefit from the speaker's remarks and from the question and answer period if you were unable to attend. Now here is the introduction to the speaker for this session.
Today with Dr. Sandeep Sarkar. Dr. Sarkar is a principal of Sarkar & Associates, a Houston-based consulting company specializing in construction materials. He has over 20 years of research and consulting experience, expertise in forensic investigation, high-performance concrete, product development, and utilization of coal combustion byproducts in the construction industry. He has over 100 publications in peer-reviewed journals, international conference proceedings. He's the editor of the book Mineral Admixtures in Cement and Concrete, and he's a member of the board of the World Cement Journal. He has his MS and PhD in Materials Science and Engineering from London University in England, and he was awarded the British Cement Makers Foundation bursary. He's held research and academic positions in various countries, including Nigeria, Libya, Iran, and Canada. Prior to joining Sarkar & Associates, he was a professor in the Civil Engineering Department at the University of Sherbrooke in Quebec. He impressed me earlier today with his command of the French language. At present, he's also associated with the Department of Civil Engineering and the Texas Department of Institute, Texas A&M University, and a guest professor and a research science, respectively. Dr. Sarkar.
Can I have the lights out, please? Lights out. What I'm going to talk today is about troubleshooting concrete problems through microscopy. What microscopy tells us is the concrete microstructure, what's inside the concrete. That's my name, and that's a company, and that's me pondering over the problems which exist in concrete. The engineer's prime concerns are, number one, how to mix concrete, how to place it, how to cure it, and to monitor its strength development to see that it achieves the desired level. Correlation between concrete microstructure and performance of concrete receives very scant attention. As a matter of fact, concrete microstructure is interpreted as being non-functional or falling outside the realm of engineering properties. The subject of my talk today is to stimulate awareness among you, ladies and gentlemen, about what microscopy and microstructure, concrete microstructure, can do in troubleshooting problems. And when I say troubleshooting, this is the type of problems I mean. I tend to divide the investigative techniques into two broad classes: direct observational techniques, optical microscopy, scanning electron microscopy, and transmission microscopy. Indirect interpretative techniques, XRD, DTA, TGA. Today, we're going to concentrate on the direct observation techniques. Optical microscopy, the first technique, is very simple, useful, and an inexpensive tool to use. It provides rapid means of diagnosing concrete, the problems, but sample preparation is elaborate, time-consuming, and often quite demanding. But optical microscopy can provide very definitive answers. Its applications in determining water-cement ratio, air content and distribution, mixture proportioning, to identify aggregates, what are the inhomogeneities in concrete, and quantification is often possible through microscopy. Scanning electron microscopy, on the other hand, allows direct observation of the concrete surface topography. You can use a very low magnification to very high magnification. It gives a three-dimensional effect because of the depth of focus. And the advantage is you can use fracture surfaces to examine. A normal concrete constituents under the SEM would look like these. You have the lime crystals, calcium hydroxide, large chunky tabular crystals. You have the aggregate paste interface. This is your aggregate. You have the lime crystals oriented at the interface. You have the hexagonal crystals of monosulfate and some primary ettringite needles. And of course, you have the principal binder material, which is calcium silicate hydrate with its fibrous growth. As you can see, this is a very porous concrete. It's also permeable. You can see all the channels. So it's basically a high water cement concrete. But this is your principal binder material of concrete, calcium silicate hydrate. Stuck. Question is, what causes defects in concrete? Actually, problems in concrete start before even you place the concrete, in the selection of materials, in proportioning, batching and mixing, design practices, construction practices, and of course, the environment plays an important role. And it can be a combination of some or all the above factors. Let's start with some improper aggregates. What would they look like? Well, they could be highly elongated, poorly gap graded, they could be dirty, they could be alkali reactive, or very porous aggregates. Elongated aggregates. As you can see, these are all elongated. The aspect ratio of these aggregates is about 4:1 or more, and it has about 40% in the mixture. Dirty aggregates. As you can see, you have the clay, fine clay particles. This is not only an elongated aggregate, but you have the clay particles, fine clay around the aggregates. This is what we call a dirty aggregate. Gap graded aggregate, you have the coarse fraction of the sand, you have the fine fraction of the sand, the medium fraction, it's deficient or missing, is the medium fraction. Reactive aggregates, strained quartz. This is the extinction of the quartz. If you move the polarizer a little bit, I don't want to go into details, you will see that you have a very short extinction. This is what we call reactive or strained quartz and can cause alkali aggregate reaction in concrete. What are the effects of using improper aggregates? The water demand increases, consolidations become difficult, you have poor paste aggregate bonding, and eventually it reduces the strength in concrete. Quality assurance failures. Let's look at some of these. Doesn't work. Very common problem is high water cement ratio of concrete. It increases the paste porosity. It produces more lime crystals, decreases strength. Final result is it affects the durability. This is the difference between high water cement. This is a high water cement concrete, and this is a dense paste with a low water cement concrete. A blue dye is used to measure the water cement concrete from the blue coloration. Now, consolidation voids. Inadequate consolidation can lead to large voids and decrease in strength in concrete. Is there another one of these? Very common failure is delamination of the concrete floor slabs. This is a core from a floor slab, and you can see the top has delaminated. And under the microscope, you might be able to see some segregation of the very fine particles, and here you have the coarser fraction. You can even see the delamination zone here. This is the top part, and this would be the bottom part with irregular air voids. If you study it carefully, you will see that you will have a dense zone, you will have a porous zone, and then you will have a normal zone. This is mainly related to some finishing problem. Air voids in concrete are very important. These are entrained air. They should be small in size, closely spaced, and uniformly distributed, as what we see here. The problem, this is what it would look under the scanning electron microscope. They're all about less than 100 microns. This is a 100 micron scale, closely distributed in the paste. The problem arises when you have agglomeration of all these. high air content in the concrete. It reduces the strength quite drastically. Additionally, when you have concentration of air voids at the aggregate interface, this is aggregate, it reduces the bond strength of the paste aggregate bonding. Retempering, very common fault. You can see a distinct gradient. You have the very dense paste and you have the extremely high water cement paste. Means adding excess water later on. And normally water is added at the job site, but when too much of it is added, then this is what you get, a gradient in the water cement ratio in the concrete. Cracking phenomena has been sort of creating a lot of research these days, because with fast track concreting practices, cracks can be a problem. There are different types of cracks. You have plastic shrinkage cracks on the surface, drying shrinkage, autogenous shrinkage, and thermal shrinkage. And these can be distinguished under the microscope. This is what you see is a drying shrinkage crack. Very short cracks, very fine cracks. Whereas this is what you call an autogenous shrinkage cracks, which occurs during the hydration of cement. You cannot avoid it. You have some hydration going, lime crystals forming. At the same time, you have the cracks forming. And then you have the thermal cracks. As you go deeper inside a mass concrete structure, you will see that the amplitude of these cracks will increase, the width will increase, the frequency will increase. And then, of course, this is what we mean by an autogenous shrinkage cracks. As you can see under the scanning electron microscope, this is what it would look like. And then, of course, you have the transgranular fractures, which is caused by some sort of movement. Usually when you have a slab movement later on, then you can have this type of cracks. Sometimes these cracks are visible on the surface, as in this case, but not always. In this case, this was what sort of told us that there might be problems with this concrete, some cracks. Just one, and here is one, two cracks. But when we investigated, we found it had a lot of these thermal cracks. Carbonation is a reaction between lime and carbon dioxide. It can be instantaneous, it can be time delayed. The result is calcium carbonate formation. It involves leaching of concrete constituents and therefore weakens the paste structure. This is an example of carbonation in a bridge. You can see the stalactite type of formation under the bridge. A very high water cement concrete ratio. Next, please. When you look at these carbonate crystals under the SEM, this is what look like: dogtooth crystal, floral distribution, globular structure, and the stacktite. They're all calcium carbonate, formed under different conditions at different times. But this is what you see in the concrete. Next, please. Efflorescence, again, is a problem. It's a migration of salts in solution. The source can be groundwater, it can be masonry. And you have precipitation of salt on the surface, and the result is problems, weakening of the structure. Next, please. This is a brick mortar structure. As you can see, efflorescence affecting the bricks and the mortar. Next, please. Some more examples. Here you can see efflorescence beginning. You can see the mortar eaten away. Here again you see some of those. You can see some scaling of the brick, and after the mortar has gone away, you can see the cracks. Mortar has been completely disintegrated. Next, please. These are, when you identify the fluorescent salt, this is one salt we found, gypsum, massive gypsum crystals. It's an expansive salt, and this is what creates the expansion and scaling on the surface of the structure. Next, please. Another type of salt we found in this case was calcium potassium sulfate or acetalite. Again, and it's an expansive salt and creates problems. You can see expansion occurring in all directions when you have this type of salt precipitation on the surface. Now, durability and deterioration of concrete are closely related. They must be considered together, and durability is the main factor in appraising deterioration of concrete. this is what we mean by the relation between durability and deterioration of concrete. I tend to divide concrete deterioration into natural. It's not an ageless material. It deteriorates over time, and this is natural deterioration. On the other hand, you have premature deterioration, and that can be due to some types of attack. It can be physico-mechanical or chemical. Physico-mechanical meaning de-icing salt, chemical meaning, for example, sulfate attack or some other form of chemical attack. Next, please. Let's look at one case study. There was only one factor involved, but had multiple effects. It was an overpass system which was constructed in 1965. The first major repair took place after 24 years in service. The clue here was it had undergone generous application of de-icing salt all throughout its service life. Next, please. When we examined the concrete, we found salts, sulfate salts, TRONA, sodium carbonate, bicarbonate, and sodium sulfate salts up to the rebar level. Beyond the rebar level, there the concrete was pretty sound. And we found tremendous corrosion. Can you lower the, yeah. And we found tremendous corrosion at the paste aggregate interface. This is the corrosion product what we see. Next, please. This is when the repair of the bridge deck was going on, repair only up to the rebar level. And this next one shows the repair of the column structure. So in this case, the problem was de-icing salt, but had multiple effects in the sense it had those expansive salt formation up to the rebar level, and you had tremendous amount of rebar corrosion. Talking about rebar corrosion, very little is reported on the microstructural characteristics of rebar corrosion, although rebar corrosion is often the key to concrete deterioration. As a matter of fact, in reinforced concrete, failure often stems from corrosion of rebar. Some of the corrosion products typically look like this. You have the tabular crystals, you have the lamellar crystals, which I showed you, and you have the delicate whiskery globular structures, which upon exerting mild pressure break. These are the types of crystals which cause major problem, exert tremendous amount of pressure, and therefore cause disintegration of the concrete at the rebar paste interface. They are mostly oxides and hydroxides of iron. They are often quite rich in chloride ions, maybe from the de-icing salt, or from, if it's a marine structure, from chloride ions from the sea. Another case study, looks can be very deceptive even in a concrete. A bridge structure, you can see the outside, it's a composite bridge, concrete and steel. Here are the abutments. It looks fine from outside. When we did an inspection of the interior parapets, this is what we saw. Somebody had repaired it at some stage. When we started breaking it, we found it just sort of falling apart everywhere. Closer look, sort of examination showed quite a network of map cracks in the concrete. We also saw that the expansion joint had closed completely. This was a very worrying factor actually. This had alkali aggregate reaction when we examined the concrete, and this is what we found. Reaction rim around the aggregates, polygonal cracking of aggregates. These are telltale signs of alkali aggregate reaction in concrete. And this is the alkali silica gel, which you can see going through the crack. When we identified, this is the alkali silica gel. This is the composition of the gel. This is what we found in the cracks, fill in the cracks. Now, we found that it had the reactive aggregates. There was adequate moisture available. There was sufficient alkalis. We don't know what the source was. It could be the cement, it could be the aggregates, but there was definite signs of alkali aggregate reaction causing all the problems. One of the recommendations was to change the expansion joint, and this is the old one. This is being replaced with a newer type. Alkali aggregate, this is another sign of alkali aggregate reaction where you have discoloration rims around aggregate particles. it still remains a formidable problem. And interesting enough, microstructural investigative techniques are the most effective tools for examining AAR-affected concrete. Sulfate attacks. Two types. Again, I tend to divide into internal attack or external sulfate attack. Internal attack is a buzzword nowadays, delayed ettringite formation. External sulfate attack could be secondary ettringite or could be gypsum. This is a case of an external concrete which has been attacked by sulfate. And you can see all the ettringite crystals in the voids. The concrete has virtually decomposed and is filled with ettringite in the surface. Delayed ettringite formation. This is a very vast subject. When it occurs, where it occurs, how it occurs, and why does it occur. I'm not going to go into all those details. I just want to show you some examples of DEF. This was a pile structure going about 45 feet inside marine piles, and we could see cracks at the water line. Some of the cracks went deeper into the mud line. When we investigated the concrete, we found these are the cracks filled with ettringite. This is delayed. The air voids filled with ettringite. The paste aggregate interface, you can see chunks of ettringite all over. This is delayed ettringite. Can cause tremendous amount of expansion in concrete, and the concrete disintegrates within a very short time. Under the SEM, these is what the ettringite crystals look like. Massive ettringite crystals, and these are the cracks formed by the ettringite. Another picture of just ettringite. Anywhere we saw, we could only see ettringite crystals. Marine concrete deterioration is another subject which is of importance to Houston. This is what you call a combination of brucite and calcite, magnesium hydroxide from salt water. Sometimes it can act as a protective membrane, natural protective membrane on the concrete. This is sulfate attack of marine concrete, forming ettringite crystals. As you can see, this is where the expansion occurs. You have chloroaluminate crystals. We are still not sure whether it has a pore blocking effect or an adverse effect. And this is what you see, increased porosity on the surface of the concrete, leaching of constituents. Lime, which is readily dissolvable, leaches out, and you have the fine aggregates which have leached out. Can I have the next carousel, please, for quickly, last few slides? Yeah. Vapor transmission in concrete is another very hot topic nowadays. Yes, vapor does transmit in concrete. It exerts a pressure. And when you see it under the microscope, this is what it looks like. You have these cracks here. This is the interface. This is where you have the adhesive, the mastic, and this is your concrete. So you can see that the concrete here at this interface has been affected. And this is where you have these channels. The vapor is coming in through here. And what happens is, at the interface, you have the water bubbles, which these were occupied by the water bubbles. The blue color means the vacant spaces now. These have been deliberately filled with a blue dye during sample preparation to bring out the voids and other sort of open spaces more clearly. As you can see, these were the spaces where were filled with water voids. And this is where it sort of passes out onto the mastic. And, next please. This is when it actually, the pressure is high enough, it breaks the mastic, and this is where the water oozes out, and it can ooze out with some of the salts as well, efflorescent salts or constituents of the dissolved constituents of the concrete. So this is vapor transmission through concrete. When you look at the same concrete below, let's say 3 or 4 inches below, we are talking about concrete slabs, you will see that the paste has been affected. All the lime has been leached out, and the paste porosity has increased. This is all leaching. This originally was occupied by some paste constituents but has leached out. So this is what vapor transmission can do to the concrete. So to conclude my presentation, up till now, technologists and engineers have mostly relied on engineering tests to determine the quality and the durability of concrete and other properties. Well, there still remain valuable tools, but nowadays increasing attention is being focused on the advantages of using microstructural investigative techniques. Next, please. I have 3 more. Microscopic examination, it provides rapid, cost-effective, reliable, and definitive answers to concrete problems. Next, please. It's a very useful tool for quality control, for quality assurance, and for failure analysis. Next, please. Next, please. Thank you, ladies and gentlemen. If you have any questions, if I can take any, I'll take them. That's all. Yes, sir.
Did you feel that these salts from sulfates and gypsum, sodium sulfates and gypsum, are actually capable of exerting enough pressure to cause damage?
Yes.
Salt crystallization growth?
Some of the salts, particularly the sulfate salts, they're highly hygroscopic. Gypsum, for example, can cause an expansion of 220% of volume expansion. Yes, sir.
You showed a slide where there was a vial in water and you saw ettringite.
That's delayed ettringite formation.
How did you, and what type of water was that? Was it seawater or fresh water?
That was seawater.
And how
But
did
it was not, ettringite was not, the sulfate ions were not coming from the seawater. Sulfate ions existed in the concrete.
But
This
how-
is the interesting part.
But how did you differentiate
Okay,
between the
what we
signs
did-
of DEF and external
What we
sulfate
did
tank?
is, we took the chemical analysis along the core, from the surface, every half inch, to determine what the level of sulfate was. We found that the level of sulfate at the exposed phase was the lowest. As we went in, the sulfate level increased. That itself was a sign. Yes, sir. Yes, sir.
Have you used XRD for some of your analyses, and how do they correlate if you have used it?
Yes, I have used particularly in identifying some of the efflorescent salts, ettringite conformation, I have used, because very analogous to ettringite is another mineral called thomsite, which is a carbonated variety of ettringite, and they both can occur. So to distinguish, to ascertain that this is ettringite, yes, I have used XRD, and also for the salts. But for alkali silica gel, for example, it's a colloidal structure. You cannot use, XRD is not very useful under the circumstances. So, but XRD certainly proves, I did not go into the details because I wanted to concentrate only on the microscopic examination. But that's a very useful, supportive tool, you know, DTA, DTG, and XRD. Yes, please. Thank you.